All right, well, let's move on to the main highlight of this evening's program. And our own Ron Payne, WA6YOU, is going to give us a very interesting demonstration of how to build a field-expedient 4-element Yagi-Uda.
Okay, we're doing field-expedient antennas. This is kind of part 2. You guys remember before we built the ground plane. Today we're going to build a 4-element Yagi made of copper tape. So for those who don't know me, I was licensed 1962 out in Livermore, California. I was a sophomore in high school, 13 years old, and I was WV6YOU. Extra class 1974 when we had to take it at the FCC. I was a radioman first class E6 in the United States submarine service. I rode the halibut and the plunger. I got out in 1970 and joined the Foreign Service, and I'm just going to list where I was able to ham. I was very, very fortunate to be able to get a license in Manila, Beirut, Lebanon, New Delhi, India for 4 years. Kathmandu, Nepal, D-Expedition, 1983. It's in QST magazine. Frankfurt, West Germany, I got a call sign, stayed 3 years, never used it once. London, England, same thing. I had a license at my uncle's house in Hampstead. Gaborone, Botswana, another D-Expedition, 1988, out in the Kalahari Desert for 2 weeks. That was a lot of fun. Mogadishu, Somalia, that was a business trip, but I managed to ham, and we were on the air during Black Hawk Down. Special events, I have 4 special events I've been on. So, guys, got some examples here of antennas. I know we're doing UHF tonight. I had some people say, hey, why aren't you building a 2-meter antenna? Hey, I brought the Honda, okay? It's too big. So we're going to build, but I'm going to give you a handout, and you can make this antenna probably from about 30 megs all the way up to a gig. I wouldn't go over 1 gigahertz. First thing we're going to talk about is other antennas, such as these. Handy talkies. It's a kludge. It's a, you know, we buy them just for convenience. Guys, we call this the rubber ducky antenna, don't we? In the industry, it's not really an antenna. It's called a linear loaded helical resonator. It's just a coil. What your radio would really like to have is this, a 19-inch whip. That's what your radio would like, but try to put that on your belt. The operator who holds these, this is your ground. You are the ground for the other quarter wave. And as you know, guys, human flesh is a pretty poor counterpoise. So what we do is we go build tiger tails. Now we will probably have a class. We did one time, Dean. We had a class to build tiger tails. I bought mine from Canada. Where's Sean? I bought mine from Canada. This is my tiger tail. So if I'm up on Skyline Drive and I want to talk to Lee on 2 meters, that's probably the way I'm going to do it, because now I've gone from about -10, -16 dB with just your radio with the ducky, and now I have does everybody see what that is? That's a half-wave dipole for 2 meters. Absolutely. And these work very well. So, I still have the old Japanese radio with a BNC, like all handy talkies should have, as a BNC instead of an SMA. And then we have mobile whips. I've actually used these at home on top of a pizza pie tin. This is a 2 meter, 20 bucks. Nice thing about this one, doesn't scratch your car. It's got Teflon. The other quarter wave is the roof of your car. Here's a quarter wave for 2 meters. The other quarter wave is actually the roof of your car, the ground plane, if you will. Okay, with that in mind, we had a wonderful class over at Dean's Garage, and we all built these. These worked like $1,000,000. I have a handout for this if anybody wants it. But one thing that all of you didn't get to see, and I'm going to go through this quick, there's a handout. Let me know if you want the handout to do the math. Again, you can build a ground plane. I've had students build this all the way up to 2 gigs. It worked. 2 gigs was an SO 239 connector. That's something you really don't want to do, but we've had them do it. So one thing I do want to show you is what we did at Dean's that day. And let's see. I got a piece of just number 12 copper wire. And I know when all of you came up here, you looked at this and went, how in the heck did you get that so straight and hard? How'd you do that? That's like perfect. This is the greatest trick you'll see probably all night. Let's see. Dean, do you feel lucky tonight? I did want to just show them this in case some of the guys hadn't been there. And we're going to put that in real hard. So what we're going to do is spin this probably 50 to 100 times until it's warm, which you don't temper copper. You can't temper copper. You can only temper steel. So we're going to work harden this. We're going to get it so hot and so many twists that the molecular structure is going to straighten out and become very stiff. You got it, okay? And I'm going to palm it. Oh, yeah. I'll stop. Okay, Dean. And I will pass that around. That's probably the best thing you'll see all night. It's a great trick. I've been doing that for many years. I've built some Yagis that way. I've built ground planes. Believe it or not, this isn't my idea. I found it online. There's a lady who has an orchid site, and she makes her orchid sticks to keep the orchids straight this way. Pretty cool. All right, guys. Next, let's do the antenna. So I have 50 color, got that, guys? Color handouts, okay? All the formulas are on there. I'm saving the history of the Yagi and some particulars about the Yagi for afterwards. I wanted to make sure we can get the antenna built first in the time allotted. And then I have 2 slides on the history of the Yagi antenna, which is a Japanese invention. Did anybody bring a calculator tonight? Okay, you don't have to. I've already done the calculations, but here's the thing. I did the calculations for 446 megahertz, which is the calling frequency for the 70 centimeter band. It makes a very, very nice small antenna. A small antenna for the classroom. You want to go home and make a 2 meter? Go right ahead. You want to make something for 220 megs? Go right ahead. The formula is good. So what we're going to do is basically lay down a dipole first. We're going to lay down the dipole. Plain old dipole. Basically a half-wave dipole for 70 centimeters. Then we're going to add on a reflector. Could you leave it that way? Yeah, sure. Driven and a reflector? Sure, why not? Then we're going to put on a second another parasitic element called a director. We're going to put that on. Could you leave it just 3? Sure. Then we're going to put on 4. And I have one in the office. I wanted to bring it in, but it's too long. I have one I made in the office. 7 elements. We put it in the anechoic chamber. It was 10.2 dBi. That thing works like $1,000,000. Okay. So here's what I'm going to do. I've already done the math. Now you probably wonder what this 30,000 K over megahertz is. 30,000 speed of light, centimeters. Remember, the answer's in centimeters. We're doing metrics, guys. I love the metric system. Yes, metrics rule, especially when you're doing antennas. Can you imagine? Cut something 17 and 47/35. You know, wow. So, the K factor. We are using foam board. This is the same foam board that you use to make your kids' science projects with. Same one. Okay? We have found that foam board has a K factor of 0.903. Have I made this antenna on anything else? Yes, I've made it on plexiglass. I've made it on the back of a door. I've made it on cardboard. Made it on all kinds of things. All of us techs in my day carried a roll of copper tape. And guys, this is not cheap. $55 for a roll of copper tape now. And the reason this is so expensive is because the stickum is RF conductive. So if I get an element too short, I can just tape right over it and it conducts the RF. I get this from DigiKey. I think even Micro Center has it. But this is just half inch I'm using. This design is for half inch. You want to try 1 inch? Go ahead. Okay. Any questions so far? You can see if you get this wrong, and you think my students ever get that top one wrong, if you get this wrong, all of these are wrong. Because everything is based on X. Element 1, the reflector, is 0.525 times that. The driven element is 0.475 times that. So if you came up with something other than 62.6 for 446 megahertz, it's wrong. So make sure if you take this sheet home and you want to build an antenna for another band, make sure you get that right. That has to be done right. Any questions? I'm just going to buzz in all the links. And like I said, let's see here. Thank God for the metric system. The gap, 6 millimeters, which is about 1/4 inch. Excellent. Okay. Couple things. Students always ask questions, so you get the list of questions over the past 20 years, and you write them down, called FAQs, frequently asked questions. Guys, make a line down the center of your board. Antennas love symmetry. Whatever on the right side should be on the left. Don't go wee-wah on all these. It'll affect the pattern. Number 2, put the driven element right in the middle. The driven element being the dipole. Put it right in the middle. I've already cut this board because I didn't want to do any cutting on their table tonight. But now, this is another question I knew somebody was going to ask. Edge to edge is the measurement for the spacing, not center to center. Edge to edge is the spacing, and we've already done that. Okay? The other question I get all the time is, do I add on 6 millimeters for the driven element because of the feed point? No, you do not. whatever I calculated, I think it's 29.7. That 6 millimeters, it's in there. And we're just going to cut that out with a razor blade. You want to make the copper tape nice and smooth? I just take a pen, take a Sharpie, something, make it nice and smooth. Please, please measure the resonant frequency of the dipole before you lay down any directors or the reflector, please. What can go wrong, they say? Shorted feed point, shorted BALUN, no pin in the BNC connector, shorted pin in the BNC connector. I mean, I've seen it all. I've seen absolutely everything I just mentioned. So always lay down the dipole, get your meter out, make sure you have a dipole for 446 megs, and then lay down your other elements. Okay? Next, cable ties. I think that's probably the second greatest invention next to the transistor is cable ties. Don't you love these things? What would we do without them? I always have a bunch of these in my toolkit. Okay, the BALUN. We're going to talk about that. I have a bazooka quarter wave shorted BALUN. My question from the engineers is always, can it touch the reflector? Yes, it can. Doesn't matter. But I still have some engineers take a piece of electrical tape and put it under here. They don't like it touching, so it can touch. Doesn't have any problems there. All right, guys. Next. This is the setup for the BALUN. This is the hardest part of the entire exercise. Can anybody explain the use of the BALUN? Why do we have it? Yeah, Lee, give us a nice explanation of why I'm even putting this on here.
We don't have time.
Okay, well, we don't have time. That's right. You know, okay, I'm going to be real simple. You know, you're right. Okay, you guys know we have a current flowing up the center of the coax, going to this side of the dipole. We have a current flowing on the inside of the braid, going up and hopefully radiating on this side of the dipole. Any reflected power is going to want to go back down on the outside of the braid. So we create a bazooka here, if you will, a shorted stub. It is shorted down in the bottom. I have scraped away some insulation on the coax and soldered this copper to it. Presents a very high impedance to any current trying to flow back down and stops it. I've already prepared these at home, but I want to make a very, very fast demo on how that's done, because this is probably one of the hardest things. And guys, when you're paying $50 for a roll of tape, so let's just take a piece of coax. RG58C, by the way, is what I'm using. And let's see, I'm just going to take something like that. I'll make sure I sweep up, Gene. Okay.
Need a third hand?
No, I'm good so far. So far. Okay. Have you got me, Jason? Okay. So.
Ron,
Better off behind, all right. Oh, yeah, that thing really does pick up, doesn't it? Huh? So guys, I have put that at a 45-degree angle. I would have marked down here 15.7 centimeters. And don't wrap the tape. Spin the coax like this. And it should be just nice. The one I passed around is perfect. And if you lose your angle, don't worry about it. Just rip it. Remember, the stickum is RF conductive. And that's how you do it, and you go right down to 15.7. Okay? Any questions on that? This is the hardest part of the day. Then when you get down to 15.7, you're going to have to cut with a razor blade very carefully, not to ding. You don't want to ding that braid. And then run a bead of solder around there. And again, don't melt the dielectric. You're going to have to be real careful. So this is usually where everybody screws this up, especially in the field because you're in a hurry or you're intoxicated or whatever. But, you know, tired, been up for hundreds of hours. Okay, so I have already made one. Perfect here. Quarter wave, soldered, and I did my pigtail. So what we're going to do here in just a minute. Were you guys here when I had the okay, I brought electric this time, Dean. Now the only thing that can happen this time is dead batteries, but so we're going to put that there, over here. So I will take my beautiful hose-on strippers. Y'all buy hose-on strippers on my recommendation? Okay. Here's another thing which really gets people. They go, oh my God, it's so short. You want it short. Because please keep in mind that as soon as the center conductor comes out of the braid, it becomes part of the antenna. Okay? All right. Okay, I guess we're ready to start our antenna. And I'm going to put this here. And I'm going to find my driven element with a D. Reflector. Okay. Has anybody worked with this copper tape before? It's pretty cool stuff. Now, another thing I don't want you to do is pull all that off because the copper tape will go brrrr. You think that happens every class? Yeah. All right. I'm going to go very easy. Easy. Okay. And I'm going to lay it down right in the center. Okay. Let me make sure here. One thing I didn't do is bend it in half to find the center. So, amazing the things you forget to do when you're up front. It's like soldering your thing in backwards. Yeah, well, we got it this time. Okay. 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 I smoothed it down. And now I'm going to take a razor blade and take out that 6 millimeters, right? And I've been doing this quite a long time, so I pretty much can eyeball that. We noticed another thing when we used to build these with cardboard. You go out to the warehouse and get some cardboard. Warehouse is damp, right? You build your antenna, everything works, and then the next morning, your antenna's been sitting overnight in an air-conditioned room, and the frequency's 20 megs off. Yeah, so that's another thing you have to think about. Let's see, where's my feed? There we go. Now, all I'm going to do is torque down one side here with and then I need somebody, Dean, I need you to hold on to this. I'll show you what we're going to do. I'm going to give you a dental pick and have you kind of press down as I solder. Okay, let's put this up, get that warm, and I'll get you a dental pick. Guys, I do recommend having somebody hold things down for you because you can use that. Kind of like a heat sink. Yeah, let's do the, okay. Yeah, just like that, Dean, great. Thanks to Lee for some solder. With lead, thank you.
Silver bearing.
Silver bearing, he didn't want to get me going on that tonight. You guys will just love how this copper tape solders. It's just beautiful. Okay, leave it down a minute, leave it down, leave it down, leave it down. Okay, let's go over to the other one. This is where the students really do a lot of shorting. They'll have one piece of hair, one piece of hair from the braid short over, ruin the whole antenna. Okay, Dean, here we go. Don't move, don't move, don't move. Don't move, don't move, don't move. And it looks like to me, thank you, looks like to me we just built a half-wave dipole. Let's see if we did. One never knows. Okay. By the way, I highly recommend this. Jesus. Dean, what's that say?
It's about 50.5 ohms.
Yeah, let's show this. 1.000000 to 1 at 50 ohms. Is that okay? All right. You know, guys have been 1.3 or 1.2, I'd been okay. But, geez. Okay. What's that tell me? Tells me I can go on now and lay down the other elements. So, let's do this one. And Dean, I would like you to, let's see, I need the reflector. He's going to lift that up. Thank you. I don't know why I didn't do that at home, you know.
Didn't have gain there.
Okay, here we go. Careful, careful, careful. Okay. Thank you, Dean. This is going much too well. By the way, guys, I want you to be careful. You see what I'm doing? Doing this? This stuff is sharp, man. This copper tape is as sharp as a razor, and I get all kinds of cuts in class. Okay. And let me lace it down with our good old cable tie. Okay, guys, can I leave it there? 2-element Yagi. Should we read the Viswire just to see what happened? You can bet it won't be 1-to-1 anymore. Okay. 1.7 to 1. 1.7 to 1, still 50 ohms. And we have a Yagi with some gain, a couple dB. All right. Next, directors. Director. Where are you? Director 1. You know what I'm going to do? I'm going to fold the other one too while we're at it. Jeez.
Bunch of critics.
Yeah, well, I appreciate it. Guys, on the Yagi antenna, I want you to consider, matter of fact, I have a little thing in my class to show how the Yagi works. The driven element, I want you to picture it as a light bulb. Light bulb. I want you to picture the reflector as a mirror, and I want you to picture each director as a magnifying glass. Okay? That's a pretty good way to. So I have one of those in class. It says this is a Yagi antenna.
Is that what director 1?
Yes, and thank you for asking. Yes, I'm putting on director number 1. Hey, you think I ever get these brought up to me backwards, fed backwards? Yeah, all the time.
How many dB gain do you get per director? Linear as you add them, or?
Well, I know that 4 elements in the anechoic chamber gives me 6 dBd, gives me 8 dBi. Okay? So there is director 1. And Dean, you were mentioning that the kids at the school had a 440 repeater. Perfect. Perfect. Okay. And director 2. And guys, there is a 4-element Yagi for 440 megs. I guess we ought to look at it on the meter, right? And by the way, I do tell them anything less than 2-to-1 is a good rig. Ooh, okay. Oh, no wonder I'm on 420 megs. There we go. Okay. I've found a lot of times they'll cut this wrong or get the spacing wrong. And even this, I think it's 29.7, and they'll bring up 30 or something, and no, you can't do that. Remember, guys, this is UHF. Every millimeter matters. Okay, we have a great antenna. Now, let's put some RF into it and see if it works. Guys, this is UHF. Every millimeter matters. Okay, we have a great antenna. Now, let's put some RF into it and see if it works. I have a meter here that I use just for 440. Got my little handy here. Noise, okay. Okay. I always forget how the sensitivity is on this. Okay. All right. Anything?
There it goes.
Okay.
Yep, that's down.
How about the back? How about the back? Anything off the wall? Off the wall? Guys, this is 2 watts. Nothing off the wall?
No.
Hot damn, look at that.
There you go.
I think we have a winner. How about cross polarization here? Not so much. Not so much. Well, I'm getting a little reflection off of these things here. I know in my classroom it's day and night. Okay. Brief history. This is a Japanese invention. Co-invented at Tokoku Imperial University in Osaka by Hidetsugo Yagi, who died in '76, and Professor Shintaro Uda, who also died in 1976, 10 years younger. The antenna was patented in 1926 in Japan, in Japanese. Dr. Yagi came to the United States, showed the antenna off at Harvard, patented in English without Professor Uda's name on it. Yeah, you heard that before? Yeah, right. The US patent calls it a variable directional electric wave generating device. Dr. Yagi called it a wave canal. And guys, last week I was looking for some information, and I was told that I should look in a 1929 IEEE bulletin. Of course, it was IRE then. So I'm joking with Lee, hey, I need a 1929 IRE bulletin, and Lee says, I got those. I went over to his house, a big thick book. I got to read the exact Yagi transcript from 1929. Fantastic. Number 3, controversy exists to this day that the antenna was actually designed by Professor Uda. But he published his findings in Japanese, and the Japanese people did not take it serious at all. Especially the Army and the Navy didn't get along, as you know. Here's the thing. Yagi lectured and demonstrated the antenna in the US and submitted his patent in English, which was immediately assigned to good old RCA. Now the kicker, how things come back and bite you right in the rear end. The Yagi antenna was not well received in Japan, and they did not use one single Yagi until 1944. The planes that came in to bomb Pearl Harbor on December 7th, we detected with radar using Yagi antennas. Both atomic bombs that we dropped on Japan had Yagi antennas, 420 megahertz, okay? 420 megahertz. That was the radar that told the bomb to go off, 1,200 feet above the target. Great story. I recommend you guys, when you go home tonight, Google Dr. Hidetsugo Yagi or Professor Uda. It's crazy. What a story. After World War II, the Yagi antenna became real popular with ham operators and, of course, TV. We were starting to build television, and TVs were on roofs. TV antennas were on roofs all over the world. Yagis. Guys, I still say Yagi-Uda out of respect for both of them. All right, guys, now, very quickly, if you want to build a Yagi, you got to pick a reason, and it's not just forward gain. There's 3 reasons you're going to build a Yagi, and each one that you pick, the other 2 are going to suffer. Number 1, this is mainly what us hams want. We want that forward gain, man. Forward one direction. When you do that, your beam width goes down a bit. Remember, the narrower the beam width, the more the gain. Number 2, front to back. Does anybody build one of these? Notice how close the reflector is to the driven. This is a DF antenna for direction finding. I got DF on here. So we built this for a great front to back. In other words, I got you. I don't hear anything. Did I give up some forward gain to get that front to back ratio? Yes, I did. No problem. All right. Number 3, the antenna I just built in class. Bandwidth. I did the 2-to-1 bandwidth on the one that I have in the classroom. Look at this, 420 to 460 megahertz. Are you kidding me? That's a 2-to-1 Viswar bandwidth. That covers the entire 70 centimeter band. So this design gives up a little of this. Matter of fact, the front to back on this is only 12 dB. Gave up a little of this maybe, but we wanted bandwidth for this design. Guys, there's so many Yagi antenna books out there. There are thousands and thousands of designs. Pick the one you want. In closing, boom length comes in. You can get wide-spaced booms, narrow-spaced, element spacing on those booms. That's another factor. Element size. You know, you might want to try 1-inch tape. Or make the driven element with 1-inch tape and then make these with 1/4-inch tape. See what that does. All these factors. And of course, we're pretty much 50 ohm people for all of our radios. So most Yagis have some kind of matching network. Gamma match, T-match. This one has a hairpin match. That's an LC circuit. There's the L, and the C is the distance between the two elements. Okay, so we have gamma match, T match. I counted 15 different ways to match a Yagi. And this is just one. This is one here. All right. That brings to a conclusion.
Fantastic.
Okay.
Thank you very much, Ron.
Thank you.
That is awesome.